The year is 1900. Physicists believe they have the universe figured out. Newton's laws govern motion. Maxwell's equations describe light. Then Max Planck enters the scene. He's studying heat radiation, a seemingly mundane problem. But Planck stumbles upon something extraordinary. He finds that energy, like light, isn't continuous. It's emitted and absorbed in tiny packets, or quanta. Imagine a beach, but instead of endless sand, there are discrete grains. This is the quantum world, a realm where energy is quantized. Planck's discovery, though seemingly minor, shattered the foundations of classical physics. It's a paradigm shift, a revolution in our understanding of the universe. The quantum era has begun, and with it, a journey into the very heart of reality. 5 years after Planck's groundbreaking work, a young Albert Einstein enters the scene. At this time, the world of physics was buzzing with new ideas and theories, but there were still many mysteries left unsolved. One such mystery was the photoelectric effect, a phenomenon that had puzzled scientists for years. He seizes upon Planck's quantum idea and uses it to explain this puzzling phenomenon, the photoelectric effect. This effect occurs when light shines on a material and causes it to emit electrons. But classical physics couldn't explain why this only happened with certain frequencies of light. Light, Einstein proposes, is not just a wave. It also exists as discrete packets of energy called photons. This was a revolutionary idea at the time, challenging the long-held belief that light behaved solely as a wave. Imagine shining a light on a metal plate. Sometimes electrons are ejected from the surface. This was known, but what wasn't understood was why this only happened with light above a certain frequency. Classical physics can't explain why this happens only at certain frequencies of light. According to classical wave theory, the energy of light should depend on its intensity, not its frequency. But Einstein's photons provide the answer. Each photon carries a specific amount of energy, which is directly proportional to the frequency of the light. This means that higher frequency light has more energetic photons. If this energy exceeds the binding energy of an electron in the metal, the electron is knocked loose. This explained why only light of certain frequencies could cause the photoelectric effect. Einstein's explanation of the photoelectric effect cemented the concept of light quanta. His work provided a crucial piece of the puzzle in understanding the dual nature of light. The idea that light can behave as both a wave and a particle, a concept known as wave-particle duality, became a cornerstone of quantum physics. This duality is fundamental to our understanding of the quantum world, influencing everything from the behavior of subatomic particles to the development of new technologies. One of the most mind-bending concepts in quantum physics is wave-particle duality. This concept has puzzled scientists for over a century and continues to be a topic of intense research and debate. It challenges our very understanding of the nature of reality and forces us to rethink the fundamental principles of physics. It states that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. This means that under certain conditions, these particles can act as discrete packets of energy, while under other conditions, they can spread out and interfere like waves. This duality challenges our classical intuition, where objects are either waves or particles, never both. In the macroscopic world we are familiar with, an object cannot be in two states at once. However, in the quantum realm, this is not only possible, but is a fundamental aspect of how particles behave. Imagine a beam of electrons passing through two slits. This is famously demonstrated in the double-slit experiment, which has become a cornerstone in the study of quantum mechanics. If electrons were purely particles, we'd expect to see two bright bands on a screen behind the slits, corresponding to the two slits they pass through. This is what classical physics would predict, but that's not what happens. Instead, we observe an interference pattern, a characteristic of waves. This pattern suggests that each electron is not just passing through one slit or the other, but is somehow passing through both slits simultaneously and interfering with itself. This means that the electrons are somehow interfering with themselves, as if each electron is passing through both slits simultaneously. This self-interference is a hallmark of wave behavior and is one of the most perplexing aspects of quantum mechanics. Wave-particle duality highlights the probabilistic nature of the quantum world. Unlike classical physics, which deals in certainties, quantum mechanics deals in probabilities. This means that we can only predict the likelihood of finding a particle in a particular place, not its exact position. We can't know with certainty the path of a particle, only the probability of finding it in a particular location. This probabilistic nature is represented by what we call a probability cloud, which shows the regions where a particle is most likely to be found. It's like rolling a dice. We know the possible outcomes, but not the exact result of each roll. This inherent unpredictability is a fundamental feature of the quantum world and continues to intrigue and challenge physicists to this day. Section 4. Heisenberg's uncertainty. Embracing the unknowable. In the quantum realm, uncertainty reigns supreme. Heisenberg's uncertainty principle, formulated by Werner Heisenberg in 1927, states that we can never simultaneously know both the position and momentum of a particle with perfect accuracy. Think of trying to pinpoint the location of a fast-moving hummingbird. The very act of observing it, perhaps by shining a light on it, alters its course. The more precisely we try to determine its position, the less we know about its momentum, and vice versa. This inherent uncertainty isn't due to limitations in our measuring instruments. It's a fundamental property of the quantum world. It tells us that there are limits to what we can know about the universe at a fundamental level. The universe is not a deterministic clockwork but a realm of probabilities and possibilities. Section 5. Entanglements embrace spooky action at a distance. Perhaps the most bizarre and intriguing phenomenon in quantum physics is entanglement. This concept has fascinated scientists and laypeople alike for decades, challenging our understanding of the universe at its most fundamental level. It occurs when two or more particles become linked, even when separated by vast distances. This linkage is not just a theoretical construct but has been demonstrated in numerous experiments showing that the particles behave as a single entity. These entangled particles share a mysterious connection. The state of one particle instantaneously influences the state of the other, regardless of the distance between them. This instantaneous connection defies our classical understanding of space and time. Imagine two coins flipped simultaneously. In the classical world, if one coin lands on heads, we instantly know the other is tails. This is a simple correlation that we can easily understand. If one coin lands on heads, we instantly know the other is tails. This is a straightforward example of classical correlation, where the outcome of one event gives us information about the other. This is a classical correlation. However, quantum entanglement goes far beyond this simple relationship. But in quantum entanglement, the coins are linked in a much deeper way. The entangled particles are not just correlated, they are in a shared state that transcends classical physics. The act of measuring the state of one particle instantly determines the state of the other, even if they are light years apart. This phenomenon suggests that information can be transmitted instantaneously, challenging the speed limit set by the speed of light. Einstein famously called entanglement spooky action at a distance because it seemed to violate the principle of locality, the idea that an object can only be influenced by its immediate surroundings. He was deeply troubled by this implication, as it seemed to contradict his theory of relativity. Entanglement has been experimentally verified, and it has profound implications for our understanding of the nature of reality and the potential for quantum computing. The ability to harness entanglement could revolutionize technology, leading to advances in secure communication, ultra-fast computing, and even new forms of sensing and measurement. As we continue to explore this enigmatic phenomenon, we may uncover deeper truths about the universe and our place within it.